Oxidation numbers. Oxidation numbers are really quite cool. Okay. Generally, when you've got a reaction and it's an ionic reaction like this, it's quite easy to see who's losing electrons and who's gaining electrons, and we went through that in the last slide. So with ionic, you know that, for instance, here magnesium's going from being magnesium with no charge to being magnesium with a 2 positive charge, thus it has to have lost electrons. So that's easy. But when it comes to an equation like this, we've got tungsten oxide reacting with hydrogen gas to form tungsten solid and water. You start scratching your head a little bit and going, not quite sure, firstly, if it is a redox reaction, and if it is, what's actually undergoing reduction and what's undergoing oxidation. So this is where oxidation numbers come into play. So oxidation numbers are used to determine whether oxidation or reduction has occurred in a chemical equation. So in other words, they are used to determine whether it's a redox reaction. So oxidation. We know that oxidation, remember oil rig, oxidation is a loss of electrons. With oxidation numbers though, when we learn how to use them, we will also be able to identify something that's undergone oxidation when it has an increase in its oxidation number. So oxidation is an increase in the oxidation number. Reduction is a gain of electrons, and it's a decrease in the oxidation number of an atom. So oxidation is an increase in the number, reduction is a decrease in the oxidation number. And that's easy to remember, reduction, decrease. So what are these oxidation numbers? Okay, there's a couple of rules that you need to remember, but once you know these couple of rules, working with oxidation numbers are really quite easy. So the first rule is that all elements, just when they're by themselves, will have an oxidation number of 0. So basically, they've got no charge to them, so the element has an oxidation number of 0. So here sodium would have an oxidation number of 0. Fluoride has an oxidation number of 0. Magnesium, 0. Nitrogen, 0. Okay? So when it's an element, it has an oxidation number of 0. First rule, that's easy. The second rule, if it's an ion, so if there's a charge on an ion like Cl -1, the oxidation number is equal to the charge on that ion. So you can see here, chlorine, -1, its oxidation number is -1. Calcium has got a 2 positive charge, and its oxidation number is +2. Another way to think of the oxidation numbers is that chlorine gains 1 electron to get a full outer shell. So chlorine's oxidation number is -1, meaning that it gains 1 electron. Calcium loses 2 electrons, so thus it has an oxidation number of +2. But don't get too confused on that. Just remember that the charge on the ion is the important thing. So if it's an element, it's got a 0 oxidation number. If it's an ion, it's got the charge on the ion. Now this is an ion by itself, not an ion in a compound. Hydrogen always has an oxidation number of 1, with the exception when it's with a metal hydride. So whenever you see it hooked up with a metal, it's got an oxidation number of -1. But otherwise it's always got an oxidation number of +1. Oxygen always has -2, which is an easy way to remember it because oxygen, or the oxide ion, has a -2 charge on it. Exceptions though are when you see it as a peroxide. So just stay aware of the fact that if you see any of these peroxides, it will have an oxidation number of -1, but they're rare. There's also another exception. When you see fluorine oxide, it also is an exception, but you'll very rarely see this. So stick to the fact that oxygen has a -2. Okay, last rule, that metals in compounds will also always have their valency. So calcium chloride, calcium is the metal, so it has a +2 oxidation number. Magnesium is the metal in a compound. Remember, it's a metal in a compound, so it has an oxidation number of +2. Sodium is the metal in the compound. Its valency is +1, thus its oxidation number will be +1. This is a point to note now. You can't know, there is no rule for the oxidation number here of chlorine in this, or of sulfur or sulfide in this compound, okay? You need to calculate these based on the metals in the compound, but I'll explain that in a minute. Don't just think though that it's the charge on the chloride ion or the charge on the sulfide ion. You need to calculate these, but I'll explain this in the next slide. The simple ion charge only applies when they're ions by themselves. So metals in compound are the valency, not the non-metals in a compound. Okay. In molecules or ions, the total sum of the oxidation numbers must be equal to the overall charge of the compound, of the element, of the polyatomic ion that we're talking about. So let's look here. Magnesium hydroxide. Let's look at our rules. Magnesium is a metal in a compound. So if we look at our table, we will see that is the charge, or the oxidation number equals the charge on that ion, which would be +2. Oxygen always has a -2, and hydrogen always has a +1. Now remember what we just said before, the overall charge of this compound, it's a neutral compound, so it has an overall charge of 0. Thus, these oxidation numbers need to add up to 0, and this is how that works. Magnesium plus 2 oxygen plus 2 times hydrogen. Now we're just adding up the oxidation numbers. So magnesium has a +2, oxygen has a +2, sorry, a -2, and there's 2 of them, and hydrogen has a +1 oxidation number, and there's 2 of those. So the overall oxidation number of the compound has to equal the charge, or the sum of the oxidation numbers need to equal the charge. So 2 minus 4 plus 2 equals 0. It's a neutral compound, thus the overall charge, or the overall sum of the oxidation numbers must equal 0. Okay. In molecules or ions, the total sum of the oxidation numbers must be equal to the overall charge. I've said this twice, I'm saying it again, this is really important. So let's look at this example here. Magnesium chloride. Magnesium, it's a metal in a compound, thus we know it has to have an oxidation number equaling its valency, which is +2. Now that we know what the oxidation number of magnesium is, we can calculate the oxidation number of the chloride ion. So we've got 1 magnesium, it has an oxidation number of +2, so magnesium contributes +2 in oxidation numbers. The overall charge of the ion, of the compound, is 0. So the overall addition of the oxidation numbers must equal 0. Magnesium contributes +2, so chloride has to contribute -2. But remember that there's 2 chloride ions. So each of those chloride ions has to contribute -1, because -1 times 2 equals -2. So chloride has an oxidation number of -1. -1 times 2 is -2, +2 for the magnesium, so +2 minus 2 equals 0, which is the overall charge of this compound. Okay, second example. Sodium sulfide, Na2S. Again, it's the metal in the compound that we can use the valency of. And we know that the oxidation number is +1. +1, there's 2 sodiums, so the overall oxidation number contributed by sodium is +2. Remember that it needs to be, the total sum of the oxidation numbers must be equal to the overall charge. The overall charge is 0. Overall charge of sodium sulfide is 0. Thus, sulfide has to contribute -2. So it has to have, because there's only one of them, a -2 oxidation number, -2. So I've got 2 sodiums, 2 times +1 is +2. 1 sulfide is -2. +2 -2 equals an overall charge of 0, an overall oxidation number of 0. So let's have a look at what happens if the overall charge of the compound is not 0, as it is here. So here we've got tetrachloroaluminate. In other words, 4 chlorine atoms attached to an aluminium. It has an overall charge of -1. So if we go through our rules, we know that aluminium is a metal in a compound, so it has to have the charge on its valency. That's fine. So we've got +3, there's 1 aluminium, so aluminium contributes an oxidation number to the compound of +3. So the overall charge on the compound is -1. So we've got +3 from the aluminium, so the chloride ions must contribute -4. +3 -4 will give us -1. So, because there are 4 chlorides, each one must contribute a -1, which will give us the -4. So, the oxidation number of chlorine is -1 in this atom, or ion. Okay, so here's a couple of examples, and it's asking you to calculate the oxidation number of the underlined atom. So first 3 are asking you to work out the sulfur. So the first rule is that an element, always when it's by itself, an element will have an oxidation number of 0. So sulfur in the first example has an oxidation number of 0. Here sulfur, which is a non-metal, so no rule applies to it when it's in a compound, is combined with oxygen. We know the rule for oxygen is that it has a -2 oxidation number. So from this we can now calculate the oxidation number of the sulfur. So the oxidation number of sulfur will equal 2 oxygens times -2, and it equals an overall charge of 0. So oxidation number of sulfur -4, which is what oxygen contributes, has to equal 0. So thus sulfur has an oxidation number of +4. +4 for sulfur, 2 times -2 is -4, equals 0. Let's have a look at this example. Remember, the overall oxidation number needs to equal the charge on the ion. Oxygen has -2, so sulfur will equal 4 times oxygen, and the overall charge of the ion equals -2, so the number, or the addition of the oxidation numbers, needs to equal -2. So sulfur, oxidation number -8, has to equal -2, so thus sulfur must be +6. +6 -8 equals -2. Oxygen -2 times 4 is -8. Sulfur then is +6. +6 -8 equals 2-. Let's have a look at carbon. Carbon is also a non-metal, so no rule applies here to carbon. So we need to work out or calculate the oxidation number based on the oxygen that it's combined with. Oxygen has an oxidation number of -2, so carbon's oxidation number plus 2 times oxygen, which is -2, will equal 0. 2 oxygens -2. That equals -4. So carbon -4 equals 0. Carbon has an oxidation number of +4. And that makes sense if you think about the electrons. Each oxygen will be will be taking 2 electrons. And where will it be taking them from? From the carbon. Here we've got carbon with 3 oxygens and a 2- charge. We need to make sure when we're looking at this carbonate that we keep into account the overall charge. So carbon plus 3 oxygens times -2 has to equal -2. So carbon minus 6 equals -2. So carbon has an oxidation number of +4 again. It doesn't always have an oxidation number of +4 though, just in those 2 examples. Okay, hopefully you're feeling confident now. Have a go. Question 1 and question 2 are in your notes. So I've got the answers here on the next couple of slides for you. So I suggest pausing this at the moment, having a little bit of a go. I'll flash up the answers for you and then I'll do some worked examples as well. Okay, so there's the answers to the first ones if you want to crack ahead. And here's question 2. Now keep in count when it's question 2 that these are ions. So the overall oxidation number has to equal the overall charge on those ions. And there's the answers to those ones there for you. Okay, I'm just going to work through these quickly. So if you know what you are doing, please feel free to fast forward along. Okay, so the rules that we know here. Hydrogen has an oxidation number of +1. So hydrogen has an oxidation number of +1. So that means that bromine must have an oxidation number of -1. +1 minus 1 equals 0, which is the overall charge. Sodium is a metal with oxygen, so we can apply both here because it's a metal with oxygen. We know that sodium has +1, oxygen has -2. +1 times 2 equals +2, -2, and that equals 0, so that's fine. Carbon, we don't know, we have to work out. Hydrogen has +1. +1 times 4 is +4. So carbon needs to have a -4 oxidation number. Sodium's in a compound, so it needs to have an oxidation number of +1. Oxygen always has -2. -2 times 3 is -6. +1 times 1 is +1. The overall has to equal 0. So that means that chlorine has to be +5. We have +1 plus 5 minus 6 equals 0. So that's fine. Aluminium is a metal in a compound, so straight away we know that it's 3+, and oxygen is -2. Let's just make sure that they add up to 0 because it's an overall charge of 0. 3 times minus is -6, and 2 times 3 positive is +6. +6 minus 6 equals 0. So that's correct. And last but not least, we've got hydrogen phosphate. We know that hydrogen always is +1 except for those exceptions. So that gives hydrogen a +3 because there's 3 of them. Oxygen is -2. That means that oxygen has an overall of -8. Phosphate must then have +5 because 3 plus 5 is 8 minus 8 equals 0, and that's what we want. Okay, just quickly on to the next answers. Nitrogen, we need to work out based on hydrogen. Hydrogen is +1. There are 2 hydrogens, so it is +2, but the overall charge has to equal -1. So nitrogen needs to be -3. -3 plus 2 equals -1. There's no reason I'm crossing them out, I just don't want you to get confused with my workings with the oxidation numbers. Oxygen -2 times 4 is -8, and the overall charge is -1. That means that manganese needs to be +7. +7 minus 8 equals -1. That's correct. Hydrogen sulfide. Hydrogen is plus 1 times 1 is plus 1 equals minus 1, which is the overall charge here. So we've got plus 1, so sulfur needs to be minus 2 because there's one of them. So if we have plus 1 minus 2, it equals minus 1. BO2 positive, overall charge of plus, so minus 2 for oxygen, minus 2 times 2 is minus 4, equals an overall charge of plus 1. So plus 5, plus 5. Plus 5 minus 4 equals minus 1. Plus 1, sorry. That's me not being able to add up. Okay, oxygen, minus 2. Minus 2 times 3 is minus 6. Overall charge equals minus 1. So iodine needs to be plus 5. Plus 5, because there's one of them, minus 6 equals minus 1. That's correct as well. And last but not least is minus 2 times 4 is minus 8. It's an overall charge of minus 3. So that means that needs to be positive 5. Positive 5 minus 8 equals minus 3. So that's correct. So that is how to assign oxidation numbers to atoms. Now we want to look at how to use those oxidation numbers. So we use oxidation numbers to identify redox reactions. If the oxidation number increases, an oxidation has occurred. If it decreases, reductions occurred. If there are no changes in oxidation numbers, it is not a redox reaction. So let's have a look at this example here. We've got hydrogen gas plus iodine gas react to form hydrogen iodide. Okay, so let's look at our rules. Hydrogen gas is an element, so it's 0. Iodine gas is an element, so it's 0. Hydrogen, always plus 1. Plus 1 for hydrogen, so iodide has to be minus 1. This is where we now look at the change in oxidation numbers. Hydrogen's gone from having an oxidation number of 0 to an oxidation number of plus 1. So it's had an increase in its oxidation number. Iodine has gone from 0 to minus 1. So it's had a decrease in oxidation number. So, the oxidation number of hydrogen has increased from 0 to plus 1, from 0 to plus 1. If it's increased, it means that hydrogen has been oxidized or undergone oxidation. The oxidation number of iodine has decreased from 0 to minus 1. 0 to minus 1. So iodine has been reduced or undergone reduction. This is therefore a redox reaction because we've had both oxidation and reduction occurring. Okay, here's a good example question which is from the very start of the video. The metal is obtained from tungsten oxide by heating it with hydrogen gas according to the equation as shown here. Using oxidation numbers, determine whether this equation represents a redox reaction, and if so, identify the oxidant and the reductant. Okay, the first thing you need to do is assign oxidation numbers. It's exactly what we've been doing. So oxygen is minus 2 times 3 is minus 6, so tungsten needs to be plus 6. Hydrogen is an element, so it has 0. Tungsten is an element, it has 0. Hydrogen, always plus 1. Oxygen, minus 2, except for those exceptions which are really rare. We just double check here. 2 times hydrogen is plus 2, minus 2 equals 0, which is the overall charge of water. Fabulous. Now it's quite simple to see what's going on. So, the oxidation number of tungsten decreases. It decreases from plus 6 to 0. So this compound is reduced. It's had a decrease in oxidation number, plus 6 to 0, so it's been reduced. The oxidation number of hydrogen increases. Hydrogen goes from being 0 to being plus 1. So it's increased, so hydrogen has therefore undergone oxidation. It's gone from 0 to plus 1. Increase in oxidation number means oxidation has occurred. The reaction is therefore a redox reaction because both reduction and oxidation has occurred. Just take note, it's actually tungsten oxide, not just the tungsten there that's been reduced. It's the whole compound that's involved in that reduction. Okay, have a go at your chapter 16 questions now, which you can do 7 to 8 in page 281.